Today we will be talking about inhibitors. Okay, so what is an inhibitor, right? So inhibitor right here. So what that does, essentially it interferes with enzymes and it decreases their rates of catalysis. Okay, so essentially interferes with enzymes and limits or decreases the rate of catalysis. You remember catalysis is just when the enzyme holds the substrate in a good position so it can react quickly. Okay, so inhibitors, essentially they stop or they kind of like make it harder for the enzyme to grab the substrate and to make it react faster. Okay, so inhibitors decrease everything. Okay, and why is this important? Well, it's important in pharmaceutical companies because some reactions can be slowed down or at least stopped with the use of inhibitors, right? For instance, like HIV, the virus. Well, if you have an inhibitor, that can slow down the reaction or can prevent the reaction from occurring. And so if we find a good inhibitor to do that, that would be very effective. That would be very good. It would save lives. So you can see that inhibitors in the pharmaceutical aspect are pretty important. Okay, so that's why we're learning it, how they function, how they react, etc. Okay, so right here we can say that some inhibitors right here, some inhibitors can either spell that wrong, can either be reversible or irreversible. Okay, so now we're dropping down into like the two sections of inhibitors, right? So some inhibitors can be reversible, meaning you can take it back, undo it, and some of them are irreversible. Okay, and we'll talk about the irreversible in a moment. So for irreversible inhibitors, we call them suicide inhibitors. Okay, so these are suicide inhibitors. Okay, I'll talk about why they're called suicide inhibitors in a few minutes. But essentially, the enzyme is going to be interacted with the inhibitor, and it's going to lose its catalytic abilities. Okay, so I'm going to just call inhibitors INH. Okay, interact with enzymes, and they covalently modify the enzyme. And covalently modify the enzyme. Now, it is that covalently modification, right, that covalent modification, that it gets rid of the catalytic abilities. Okay, so whenever the enzyme is covalently modified, that's permanent. It cannot go back, and the inhibitor has done its job. It essentially took the enzyme that was healthy and it changed some covalent bonds, and then it ruined the enzyme. So the enzyme can no longer do a reaction, right? It's permanently like that. Okay, so this is permanent. This is permanent. Okay, so you can see how irreversible inhibitors are kind of important if you're working in pharmaceuticals. They're also very prominent within weapons. So for instance, you can see them in nerve gas or the VX gas, and they're even in aspirin, right? And so aspirins, they target certain parts of your body, right? And they are going to react with the enzymes that kind of register pain and whatnot, and so they take out those enzymes so you don't feel pain. Of course, your body makes more enzymes, but that's what aspirin does, right? So suicide inhibitors are called that because it's kind of suicidal for the enzyme to interact with the inhibitor because it's going to lose its catalytic ability. And again, this is very prominent within nerve gas, VX gas, right? Yeah, so there you go. That was it, and now we're going to be talking about reversible inhibitors. So let me clear the screen. So reversible inhibitors. So there's about 3 classes of inhibitors, but first we're going to talk about what it is, right? So reversible, I mean. So essentially it binds to an enzyme and it limits its ability to be a catalyst, right? So if you imagine like an enzyme to be a power outlet, okay? And then you recently had a kid, maybe you're babysitting. Well, you would buy those little outlet covers so the baby won't stick like a fork into the outlet, right? And hurt itself. And so what you're doing is that the outlet cover is the reversible inhibitor, okay? You stick the little plastic cover into the outlet so the baby with its fork, you know, it's not going to be able to shock itself, right? So you can always take off the plastic cover, right? So that's going to be like a reversible inhibitor. They go into the enzyme and they prevent anything from coming in, right? So the substrate, the little baby, won't be able to jack its fork into the outlet and hurt itself, okay? So you can say that reversible inhibitors bind to the enzyme but can come off. But can come off. And they limit or they even stop the enzyme's catalytic ability. Okay, and there is no covalent changes or modifications. No covalent modifications. Okay, so for instance, for non-reversible inhibitors, that's like demolishing an outlet and plastering over it. Okay, so you took out the whole outlet and you just repaired the wall. There's no more outlet. You can never use that area again. That's for non-reversible inhibitors or irreversible. And then reversible inhibitors, it's like a power outlet cover. You can take it off. It's going to stop the reactions when it's in, etc. Okay, so now we're going to go into the 3 classes. We can go to the 3 classes of them, and some of them are competitive. The other is non-competitive. And the last one is going to be called uncompetitive. Right? So there you go, and I forgot an I right there. Okay, so there are 3 classes of reversible inhibitors, and so this video is going to be focusing on the 3, right? And we're going to have some graphs to go along with it. Right, so competitive inhibitors, right? So first of all, notice that the inhibitor I is very, very similar to the active site. Okay, so inhibitors, in general, inhibitors tend to look like the active site. They tend to kind of fit, right? So inhibitors look similar to the substrates. and fit in the active site. Okay, there we go. So now, whenever the inhibitor, so first of all, the enzyme is going to show up, right? And it wants to take the substrate in order to do the reaction. And so it's kind of like playing musical chairs, right? There's only one chair, one enzyme, and there's two people. Well, the inhibitor is going to steal that enzyme, and it's going to take its place. Now the substrate, let's do this. The substrate is going to want to go in here, but it can't, right? Because it's being blocked by the inhibitor. And so therefore the reaction cannot take place. Of course, whenever the reaction is done, the inhibitor can get out of the enzyme and go on with its day, right? It's not permanent, it's just taking its place. So another way you can view it, if you like flowcharts, I guess, is that the enzyme, let's do a better E, that the enzyme plus the substrate is going to give you the ES, and that's going to give you the E product, right? But this can also go here, right? We can have the inhibitor. And so you can have the inhibitor plus the enzyme times the enzyme plus the substrate is no reaction. So let's recap. Well, normally you want to go to this route, right? The top part of it. So the enzyme plus the substrate gives you the ES complex, which then gives you the enzyme in the product. But the enzyme can also be taken by the inhibitor. And when that happens, you have the enzyme times the inhibitor plus the substrate. But now the enzyme cannot do the reaction because its active site is being taken by the inhibitor, so there's no reaction, okay? Most pharmaceutical drugs are competitive inhibitors, okay? So they actually fight for the enzymes. They don't physically fight, they just kind of try to react faster with the enzyme than the substrate. Now we're going to be talking about, graphs, right? So for every class of inhibitor, there is a graph, okay? So specifically, we're going to be talking about the Lineweaver-Burke graphs. Notice that this isn't necessarily a straight line graph. It's kind of like a hyperbola, which is modified. I just feel like these graphs, you can actually tell what's going on easily. The line graphs don't really help, but the idea is still the same, okay? So again, that's why we covered Lineweaver-Burke equations, okay? Because of this. So for competitive inhibitors, we'll call them CIs, okay? For competitive inhibitors, notice that without the inhibitor and with the inhibitor, the Vmax stayed the same, okay? So Vmax stays the same, okay? So let's put same. Okay. Now, for every class of inhibitor, you can tell what it is, what kind it is, if you were given a graph. So for instance, if you were given a graph that has some information like this, without the words, you would say, okay, well, without the inhibitor and with the inhibitor, my Vmax stays the same. Here's some other information. Okay, I know that this is going to be competitive. Oh, I know this is going to be non-competitive. I know that this is going to be uncompetitive, etc. Okay, so you can base the type of inhibitor by the kinetics. Okay, so Vmax stays the same, but notice over here, notice something kind of peculiar, that the Km, the affinity, the love for the substrate by the enzyme, actually increases as we add inhibitors. Why is that? Okay, well, again, here's my enzyme, right? And let's say that we have an inhibitor, okay? Okay. Well, is my enzyme going to want to bond with this substrate? Right? No, it's not going to want to bind to that substrate because its active site is already taken by the inhibitor. Therefore, the want for enzyme to bind with the substrate decreases, okay? And whenever the want for the enzyme to bond with the substrate decreases, the Km increases, okay? Remember that a large Km means a very loose and sloppy binding energy, okay? It doesn't want to bind with the substrate. If you have a very small Km, it wants to bind with the substrate. It's going to actually seek it out. But with the inhibitor, the Km increases. And that makes sense because its active site is already occupied and it doesn't want anything else. It's not going to want to go to the substrate. So we can say that the Km increases. And yes, notice something, that the Vmax stayed the same. You're probably wondering, hey, Brian, isn't it supposed to decrease? Why is it able to stay the same, yet the Km increases? Well, that's a good idea. Hold on to that idea and I'll explain it to you. The reason why we can actually achieve our maximum velocity, even though the Km is increasing, is because we can add a larger amount of substrates, okay? So, yeah, you have a 1-to-1 inhibitor to substrate, but what if we add more substrates? What if we did that? Then, if you have 5 substrates for every 1 inhibitor, are your chances of a substrate going into the active site of the enzyme higher? Yeah, they are. You have a higher chance of a substrate connecting with the enzyme and carrying out the reaction. Well, that makes sense, right? So, because you have more substrates, they can actually compete against the inhibitor and occupy the enzyme like 9 times out of 10 if you have more substrates than inhibitors. So, if you increase the substrate, you can overcome the inhibitor. Okay, so you can actually do the reaction. Okay, so yeah, that's about it. I think, yeah. So for recap, the Vmax stays the same. The Km increases, meaning that the enzyme doesn't want to interact with the substrate. And then for competitive inhibitors, you can actually overcome them by increasing the amount of concentration of substrates in the environment. Okay, so if you increase the amount of substrates in the environment, you can overcome the inhibitors and carry out the reactions. Now this is actually a non-competitive inhibitor. So these are non-competitive inhibitors. Okay, so essentially you have an enzyme that has 2 kind of like binding sites, right? So one portion, the substrate is going to go into the active site and carry out the reaction as normal, okay? But sometimes the enzyme reacts with the inhibitor first, okay? And then the substrate goes into the other active site. Now, whenever you have both in one enzyme, well, the reaction is not going to happen, right? But notice that the inhibitor didn't have to compete. There are 2 chairs and 2 people, okay? So there's more than one active site, okay? So what I'm trying to say is that the inhibitor does not need to go faster than the substrate to get the last spot in the enzyme. That's not the case. There are 2 binding sites, so it doesn't matter if the substrate comes first or the inhibitor comes first, whatever. They're both eventually going to go into the enzyme, and that reaction is not going to occur, right? So what happens when the inhibitor binds to the enzyme? Well, the inhibitor, whenever it binds to the enzyme, is actually going to change the active site. So look, this substrate was here first, and then an inhibitor came into the binding site. So now the enzyme kind of squeezed together the walls, and it popped out the substrate. So now the substrate is still in contact with the enzyme, right? But, hey, it can't react. The inhibitor is preventing the reaction from occurring, okay? So you should know that non-competitive inhibitors, they change the shape of the active site once they're binded. Okay, so it's really not that hard of a concept to grasp. And now we will go into the chart. Here's a chart for the non-competitive inhibitors. So this is non-CI. Now, notice something. Notice that the Km stayed the same for both the enzyme without the inhibitor and the enzyme with the inhibitor. Why is that? Well, remember that Km is just how much the enzyme wants to bind with the substrate, right? But in a non-competitive inhibitor environment, well, the enzyme is always going to bind with the substrate, and it's going to have one more active site for the inhibitor. So whether the inhibitor joined the enzyme or not, the enzyme is still going to want the substrate, right? So again, let's just draw, I don't know, like this weird shape, right? So whether we have the inhibitor right here, it doesn't matter, because we still have one more spot in which the substrate can come in and do its binding with the enzyme, right? So the enzyme is still going to want the substrate. That's its homie, you know, that's the homeboy. We gotta, you know, hang out. But yeah, that's the homie. So, you know, it doesn't matter if the inhibitor is there. So therefore, Km stays the same. Right, so it stays the same. That's kind of weird. Okay, so notice on that portion the Km stayed the same. But what did change? Well, what did change was the maximum velocity of the reaction. And this happens because, well, look. Let's say that the enzyme binded with the substrate first. Okay, so it's doing its reaction. It's going as fast as it can, okay? But then the inhibitor kind of piggybacks midway, right? And that reaction is going to slow down and eventually stop. It's similar to kind of like a track runner running. You know, he's going the distance, and then all of a sudden, someone throws a huge baby pig at him, and now he has to carry that pig into the finish line. Do you think adding 70 pounds to that track runner's weight is going to help him go faster? No. So adding an inhibitor halfway through the reaction, when the enzyme is binded with the substrate, is going to slow it down. It's going to slow down the maximum velocity, and that's not good, okay? So we can say that the Vmax can actually go down. Okay, there you go. So Vmax goes down, right? So it's very it's not similar to the competitive inhibitors, because competitive inhibitors, if you recall correctly, the Vmax stayed the same, and then the Km went up. Well, this one is kind of the opposite. The Vmax goes down and the Km stays the same, okay? And also, what's different between those two is that no matter how many substrates you add, it won't matter, because the enzyme is still going to have that one extra spot for the inhibitor, and it doesn't matter how many substrates you have, the inhibitor is still going to, you know, bind with the enzyme. So cannot, so we're just going to put cannot overcome inhibitor with increasing concentration of substrates, okay? So remember, you cannot just increase the substrate and expect the reactions to keep going. No, the inhibitor is still going to have that one little spot, and the enzyme is going to bind with it and stop the reaction completely. It's going to slow it down and eventually stop it. So there you go. That's how you read the chart. So here's kind of a bonus for you guys, okay? So this is still non-competitive inhibitors, but there's a different kind, okay? So there are two kinds. This one is called mixed inhibition, okay? So non-competitive inhibitors, subclass mixed. Mixed inhibitors. So what is that? Well, notice that there's an enzyme, okay? There's an enzyme, and here's the active site. Well, let's say that the inhibitor goes here first, okay? It went to a location on the enzyme that isn't a binding site. That's very important. It went to a location on the enzyme that is not a binding site. Okay, let's just say that it picked this location. Okay, let's just say this little flat part. Well, then the substrate moseys along and connects itself to the enzyme. All right, so whoop-de-doo, it's the same thing as non-competitive inhibitors. Well, the difference is that the Km actually increases. So that is the most important thing. So everything is the same between non-competitive and mixed inhibitors. Everything's the same except the Km increases for mixed inhibitors. Okay, so Km increases. And that's so weird, right? Like, you know, the Km, well, not actually, that's not weird. The Km should increase, right? Because it doesn't want to bind with the substrate anymore, which is kind of weird, but yeah, I digress. So everything is the same. Except Km increases. So let's write that. Hold on. Except Km increases. And there we go. So that is another type of non-competitive inhibitor. So if you see that the Vmax decreases but also the Km increases, well, that's a non-competitive inhibitor, but it's mixed. Okay, it's a mixed inhibitor. And like before, it doesn't matter how much substrates you have, it's still going to happen. Okay, so the only difference is that the inhibitor binds to a different part of the substrate. Okay, so there you go. For the last class of inhibitor, this is going to be the uncompetitive inhibitor. Okay, so this is uncompetitive. As you can see, you have the enzyme, you have the substrate, and then you're going to have the enzyme substrate inhibitor. But let's get into it. Okay, so we have the uncompetitive inhibitor. Now, the uncompetitive inhibitor actually only binds with the enzyme after the substrate is bound with the enzyme. Okay, so let's write that down. Binds with enzyme only after the substrate is bound to the enzyme. Okay, so I think, if it's kind of annoying how this happens. It's like if I give you a real world example, let's say that you're sitting on a bus, okay, and there are no seats left and you got the last seat, and someone gets on the bus, looks directly at you, and goes next to you and sits right on top of you, right on your lap. That's really annoying, right? Now you're having a very uncomfortable time, and you're in the middle of going to your destination. Now that's a drag for real. So likewise, the enzyme is going to bind itself with the substrate, and they're very happy. They're going to do the reaction, but halfway through the reaction, the inhibitor just shoves itself right into the enzyme and ruins everything. It ruins it. If you want to see it as a reaction equation, you can put the E plus S can go to the ES. Let's do this. We can go to the ES complex, and we can also make the EP, the enzyme in the product. But sometimes this happens where the inhibitor joins in halfway, so now you have the ESI, and we know that the ESI is never going to make a product. Okay, so yeah, it's very annoying how that happens, right? So it only happens when the substrate is bound with the enzyme, okay? So let's look at the Lineweaver-Burke graph. Okay, so notice that the pink is going to be with the inhibitor. Okay, so naturally, you can see that the Km actually decreased. Isn't that weird? That the affinity for the enzyme with the substrate actually decreased. So the enzyme wants to grab more substrates. That's kind of weird, right? Well, it makes sense if you think of it like this. So at first, the enzyme is going to want to attract substrates because it doesn't have anything in it. So it's going to connect with the substrate. That's pretty normal. But then the inhibitor is going to join in, and that ruins everything. So perhaps the enzyme it wants to seek out more substrates because it has this gap in it. It has this kind of wedge in it, and it wants to get rid of the inhibitor, and it's trying to search for a substrate to get rid of the inhibitor. That's my theory. That is what helps me make sense of this, right? So yeah, the Km actually decreases. So Km decreases, right? So enzyme wants more substrate. Okay? Wants more substrate. Now what about the maximum velocity? Well, understandably, the maximum velocity goes down. Why is that? Well, again, think about the track runner. Let's say he's trying to run a marathon. So halfway through the marathon, he's doing very well. But halfway, one of his sponsors is like, we're being sponsored by a farmer, and he wants you to carry one of his prize-winning pigs to the finish line. So halfway through the marathon, the runner gets tracked. He's given a pig, and now he has to run the extra 13 miles to the finish line. Is he going to run it at the same pace at his maximum velocity? No. Now he has to carry that pig to the finish line, and it's going to take a longer time. He may not even make it. Okay? So likewise, halfway through the reaction, the ES complex is introduced to the inhibitor, and now that inhibitor is preventing it from completing the reaction. So now the reaction is going to take a longer time to complete or not complete at all. Okay? So the Vmax goes down. Okay? And going back to the bus example, it doesn't matter if you have more seats available on the bus. You could be the only person on the bus. But that one person is going to look at you and sit right on your lap and ruin your day. Because that's just how they are. The inhibitor doesn't care that, there's more substrates available or whatever. It's still going to shove itself into the enzyme with the substrate. Okay, so cannot be overcome with increasing S. Okay, so yeah, that's about it for the inhibitors. Finally, I want to talk about coenzymes. So what are coenzymes? They sound pretty cool. Well, sometimes an enzyme wants to do a reaction, but it needs a little pick-me-up to do it. So coenzymes essentially attach themselves to the enzyme with non-covalent bonds, okay? And they help out the enzyme to interact with the substrate, okay? So sometimes the enzyme needs a little bit of help. The coenzyme is right there. That's the co-pilot, okay? So they bind to enzymes to help out in a reaction. Okay, and this is a non-covalent bonding. Of course, there's always an exception to everything. So the exception are going to be prosthetic groups. Prosthetic groups, if you remember correctly, they're just like little, they're essentially like metal ions. They could be metals that covalently bond to the enzyme. Prosthetic groups are the exception. And covalently bond to the enzyme. Okay, so prosthetic groups are also coenzymes, okay? So what exactly is a coenzyme? I'm pretty sure you had some today, because coenzymes are a majority of the vitamins. For instance, vitamin A or vitamin K, those are coenzymes, okay? And so they help out in reactions. And coenzymes can be regenerated after a reaction is completed, so they can be reused later on. So we can put can be regenerated. What else can coenzymes do? Well, coenzymes can regulate the enzyme activity, okay? So how can they regulate the enzyme? Well, one way that they can actually regulate enzyme activity is by doing inducing. They can induce something, they can make something happen, or they can reduce something, right? So they can induce and reduce. Okay, how can they do that? Well, for instance, they want to kind of keep a close eye on how many reactions are occurring. So if too many enzyme reactions are occurring at once, the coenzyme is going to say, hey, you need to chill out, you need to stop doing this. And likewise, if not a lot of reactions are occurring, it says, hey, we got to pick up the pace, we have to start doing some more reactions, right? And one way that it can do that is say that, cell A has more enzymes than cell B. Well, that means that cell A is going to have more reactions going on. So the coenzyme looks at it and says, hey, you know what? You need to chill out. Like half of you enzymes go to cell B, and we're going to have an equal amount of enzymes, okay? So now we're going to be doing equal amounts of reactions, okay? So we can actually stop. We can stop or increase the amount of reactions of enzyme reactions. Okay, and we can also move around enzymes to different cells. Can move enzymes to different cells. Okay, so that's pretty cool. That's pretty powerful. But it's power hungry. It doesn't want to stop there. What coenzymes can also do is that they can essentially modify intrinsic properties of the enzyme. So the enzyme has some information built into it to tell it what to do. Well, the coenzyme can go into the enzyme and change what it can do, okay? And it can actually make non-covalent interactions with proteins, lipids, and some other small molecules, and it can do it reversibly. So you can say that coenzymes can also change how enzymes operate. Okay, and they can make the enzyme bind with proteins, lipids, or other small molecules, and it can actually reverse it. So once it binds to something, it can get off of that molecule, right? So it's not permanent. So can make bind with lipids, proteins, let's put etc. And this is can be reversed. Okay, so that's pretty cool too. Coenzymes can also do reversible covalent modifications. An example could be phosphorylation, methylation, and the creation or breaking of disulfide bonds. Okay, so phosphorylation can occur with serine, tyrosine, or threonine. So serine, tyrosine, or threonine, right? Methylation, it's not really important. It's like it shows up whenever you want to make a bacteria glow in food, right? So that's just kind of like a science thing. It can also be in the process of creation or breaking disulfide bonds. Okay, so for instance, like hair, you're going to be breaking a disulfide bond whenever you're trying to change the shape of the hair at a beauty salon. So coenzymes can be used to do that as well. But of course, these can be reversible processes. Okay, so now we're at the last stretch of talking about coenzymes. So coenzymes, again, they can do a lot, right? It's crazy. Well, here's a series of words that are very long and arduous and make no sense whatsoever. Okay, so here is isoprenylation, comma, acylation, and palmite, actually this is an O, palmitoylation. What does that mean? Ugh, it's like alphabet soup. It's just a train wreck. Well, it's actually just the addition of fatty acids. Now, it's safe to say that this, whenever you add a fatty acid, it's going to be irreversible. So the following are going to be irreversible. Irreversible covalent modifications. Okay? Does because these are irreversible covalent modifications. So in a textbook or on an exam, I don't know if it's going to be there, but if you see isoprenylation, acylation, or palmitoylation, so essentially anything with ylation, let's add that note right there because that's a very common trend. So anything with ylation, and specifically with coenzymes, you know it's going to be irreversible. You're going to be adding a fatty acid, okay? So that's it, right? Now, the only thing, there's an exception to everything, right, is going to be the glycosylation. Do you know what that means? Well, ylation means we're going to be adding something that's going to be irreversible, but this is just what? Sugar addition. To what? To asparagine. Asparagine. Let's put 2, I forgot the 2 right here. So it's very specific, but glycosylation is just the sugar addition to asparagine. Okay, so not much to say about that, but that's it. So also, the last thing we're going to talk about is called proteolytic cleavage. Okay, so what is that? So essentially, zymogens are essentially the inactive precursor to an enzyme. So when an enzyme is not active, when it's still forming in its little baby cocoon, we call that a zymogen, okay? So zymogen is like a pre-birth. It's not really born. I guess we're just using that example. So it's like a prototype enzyme. It's the enzyme before it becomes an enzyme. So that's called a zymogen, right? So zymogens are essentially they're activated by the cleavage at a specific peptide bond, okay? Are activated by cleavage at a specific peptide bond, okay? So why is that important? Well, depending on the environment at which the zymogen is held, for instance, in the pancreas, if they were activated in pancreas, that could be lethal. You could die from the zymogen activating in the pancreas. You don't want that happening. So where do we want the zymogens to activate? Well, you want zymogens in the small intestines. Small intestines. Okay? Because they're going to be interacting with proteins, and you don't want them to interact with your pancreas proteins. You do not want that happening. You do want them interacting with the proteins in the food, though, because then you can extract nutrients, and that can be passed into the small intestines. Okay? So there you go. Hopefully this video helped you out in understanding coenzymes, inhibitors, and the charts that go along with the inhibitors. I hope you have a great day, and I really appreciate you spending time with me learning. Remember that I love you and that you can pass your exams. All right, take care.